Greetings and welcome, friends. Mr. Wada here. We were talking about dilations yesterday, which is basically a non-rigid transformation. It's a similar transformation as we'll talk about today. But yes, so dilations reduce or enlarge an object by a scale factor. And yeah, let's see what we got here. So it says find the scale factor of the dilation. So it's going from P to P prime. It's going that way. And to find the scale factor k, it's always going to be the distance that P prime is from your center of dilation over the distance that your pre-image was from the center of dilation. It looks like both of those are reducible by 3. So this is a scale factor of 8/3. And because 8/3 is larger than 1, this will be an enlargement. Enlargement, yeah. There you go. There you go, friends. Not bad, not bad. Aha. All right, so let's see. Here, I want to do a coordinate plane dilation, and fortunately, this is super convenient the way this works out. If I want to find t prime, for instance, I'm literally going to just take the scale factor of 2/3 and multiply it by both of the x and the y coordinates. So 2/3 of 9, comma 2/3 of -3. So that's going to become t prime being 9 divided by 3 is 3. 3 times 2 is 6. And -3 divided by 3 is -1 times 2 is -2. So over 6 down 2 is going to be t prime here. And you notice that it's actually, it's going to be 2/3. If I was to break this into thirds for this distance, it's 2/3 of the way to t. So it was, in fact, a reduction. I won't do this work for all of them. We'll just recalculate. So 2/3 of 6 is going to be 4. 2/3 of 0 is 0. So that's going to be over 4. So here's u prime. V prime, 2/3 of 3 is 2, and 2/3 of 9 is 6. So over 2 up 6, and so here's v prime, and it's 2/3 of the distance there. And a dub prime, 2/3 of 0 is 0 for both of those. And so if a point is on the center of dilation, it gets mapped to itself. Let's see. Man, some of these lines I'm not good at drawing. There we go. Something like that is what it is, and that is all of its linear dimensions, so its sides are 2/3 the side lengths of the original quadrilateral. Its perimeter is 2/3 because perimeter is just the sum of those sides, and its area would actually be 4/9. But you don't have to worry about the area thing until, like, I think it's chapter 8 or something like that. All right, it's also possible to have a scale factor that's negative, and that was the same as doing a scale factor by the absolute value or the positive version of this, and then a 180-degree rotation. So L prime, the math is exactly the same. 0 times 0 is 0, or sorry, 0 times -3 is 0. So L prime is going to be in the same spot. M prime is just going to be -3 times -4, which is +12. -3 times 1 is -3. So over 12 down 3. And so this is on the opposite side of the center of dilation, but it's 3 times away, is one of the ways you could think about that. N prime is going to be -3 times -3 is +9 and +18. So over 9 up 18. Thank you, past self, for giving me this conveniently pre-made grid. So yeah, so this object will be 3 times all of its linear dimensions and 9 times the area. Okay, so let's see. So the red figure in my case is the blue one, because I inverted the colors, and the blue figure is the orange one, oddly enough. Let's see. So there we go. So it looks like the dilation is mapping it in this direction. So it looks like it's a reduction. It says find the scale factor of the dilation. So k is going to be 14 over 28, which is 1/2. All right, so it's a 1/2 reduction. And if the side length of this original side was 12, the side length of this, n, is going to be 1/2 of 12. So n is going to equal 6. So that's one way you could kind of use the scale factor to figure it out. You also will eventually, I believe today, we're going to work with proportions. So I also could have set it up in an alternate universe approach. I could have said that n is to 12, all right? So the little is to the big as the little is to the big, as 14 is to 28. And then if I reduced that, n twelfths equals 1/2. And then you could even either cross multiply, or you could just multiply both sides by 12. But using proportions would work as well and give you the same result. And I think that proportions require less thinking. This kind of requires me to make sure, all right, am I multiplying it the right way? Should I divide by the scale factor? This you just kind of set up like things comparing to like things, and it all works out. Let's see. Oh dear. Oh dear. Let's see. This will be fun. I'm pumped. Oh, nice. My compass tool is, oh, that's an 83 degree. Oh man, how terrible. That is not a circle. There we go. There we go. Now that's a circle. You believe it. I believe it. All right. So this is the idea. I want to do a 25% reduction of this triangle by center C. So let's see. So I think let's start with line L for Liam, maybe. Yeah, Liam Math, LM, Liam Math. I think this is like a subliminal messaging here. Yeah. So there's that. Now, if I want to do a 25% reduction, the only way I know how to do that is to do the midpoint of a midpoint. Oh, that was weird. So I'm going to arc this past what I perceive is the midpoint. All right, and make a perpendicular bisector here. Leaving that radius the same, I'll bring this over to the other side. Oh yeah, just enough space there. Not bad at all. Like so. Let's see, I think I can scale this down a little bit. Oh, actually I still need to use that in a minute, but that's okay. All right, and so I'm going to construct the perpendicular bisector, suggesting that this point is the midpoint. So this would be a 50% reduction of L, but we want to do that again. So lining up at that point, do a second perpendicular bisector. We'll go a little bit further over there, keeping the radius the same. The trick is just you have to make sure that your compass tool is going past your perceived midpoint. Otherwise, these two arcs won't intersect, and it won't help you create a perpendicular bisector. So that is going to be L prime right there. So it's so this would have been 50%. Half of 50% is 25%. If you were looking for 3/4, you could have found this point here and do a 75% reduction. Let's see. I'll do one more just for good measure, but I think I'm gonna take the lazy man's. Yeah, I'll take the lazy man's way out. Which also, I just happen to notice that LM stands for lazy man. I'm just kidding. This is just competitive, YouTube math channeling here, or Liam math, right? No, just hey, I don't know, just no comment there. I don't know what I'm trying to say. Competitive advertising. All right. Yeah, I do zero editing. This is all raw. This is real and live. Yeah, maybe not. Let's see. Looks like I needed to make that arc a little bit bigger. All right, so there's one perpendicular bisector. Actually, this isn't bad. It gives us some practice with perpendicular bisectors all over again. And I don't even have to finish the line tool. I just needed that point there, right? And then I will doubly perpendicular bisect it. So let's see, right about there. Rip. And so split the split. Like that, like that. And these should be parallel because they're both perpendicular to the same line. Was that perpendicular transversals theorem or something? Something like that. Liam Math would know. Let's see. So there's M prime. That's a 25% reduction. And so I will point out that M prime to L prime is also going to be 25% of the distance or the segment length of the original M to L. All right. Yeah. This is a lot of work. When I could have just done something like this and just been like, whoop, whoop, and then like when I paste it, I don't know, scale it down or something. But that's actually not going to be right either because it pasted it at more pixels than I had. I don't know, something, bam, not really. All right, well, anyways, I'm not going to finish that problem. Thanks for watching, Internet friends. We have a test tomorrow. I want to make sure we have time to invest in that. Bye-bye.